for the introduction. Hi, I'm Henning from TU Dortmund University. This work is on analytical query processing on coprocessors with a focus on GPUs. It's joint work with Sebastian Bress from DFKI, Stefan Noll and Jens Teubner from TU Dortmund University, and Volker Markel from TU Berlin. So let's have a look how relational operators for a query are usually executed on GPUs. Usually the I/O for each operator is transferred separately for each operator. Operators here can be are usually sub-operators because relational operators consist of multiple steps, and each of these steps is implemented in state-of-the-art systems with separate I/O, leading to a big amount of PCIe traffic because that's like the channel for communication. And for example, for the star schema benchmark query 3.3, SSB 3.3 and so on. This leads to a traffic of 8 gigabytes in total, which corresponds to a transfer time of 350 milliseconds. By reorganizing this with a simple technique, we can keep the intermediate batch results on the coprocessor and pick them up instead of transferring back. This works when intermediate batch results like hash tables have enough space on the coprocessor. And in this way, we reduce the amount of the transfer volume by from 8 gigabytes to 0.9 gigabytes, which is a big reduction in transfer time to 31 milliseconds. And although this is a simple technique, it has a big effect, and we can see that when it's applied, actually, PCI Express is not the bottleneck at all. Actually, the execution time on the coprocessor for SSB 3.3 takes much longer, here 180 milliseconds, than the transfer time. So why does the kernel execution take so much time? As I said, each relational operator is usually implemented from sub-operators that are necessary to work in data parallel. And each of these sub-operators has its individual global memory I/O to the memory on the coprocessor. And for example, a really simple select and aggregate query, like a low number of filters, and aggregation takes already 13 kernels. And this is actually what causes the GPU global memory bottleneck, which is actually the case for a lot of queries after when doing PCI Express transfers in the right way. So how can we address this? A commonplace way to improve the memory efficiency is to use just-in-time compilation. But for GPU processing, the multipass processing style, which splits each operation into multiple steps, contradicts the sequential tight loop processing style that we see for just-in-time query compilation. This leaves us with a conflict. We would like to save bandwidth and use just-in-time compilation, but to use this fine-grained way of parallelism on the GPU, we need synchronization and have to do this traditional multipass processing. And to address this, we use a non-blocking prefix sum implementation, which allows it to eliminate these additional pipeline breakers in parallel GPU processing. The non-blocking prefix sum is maybe not the best performing implementation for a prefix sum, but we trade a compute overhead for a big increase in bandwidth efficiency, which finally outweighs this issue. And in this way, we minimize the synchronization, so we don't globally synchronize whenever possible. We skip global synchronization. Let's have a look at the effect, what happens when we apply this. Here we have 3 different settings for a query with 4 relational operators. In a classical setting, each relational operator is executed with 3 kernels with an intermediate prefix sum, and we have a memory access volume on the coprocessor of 8.4 gigabytes for star schema benchmark query 3.3. When we apply compilation in a naive way and just merge the kernels within each of the sub-operators, then we get a limited benefit, and we can process each operator pipeline with 3 kernels, leading to 6 kernels, and we have a limited benefit in memory access to 4.4 gigabytes. But when we pipeline the prefix sum computation, we can actually substantially reduce the amount of bus transfers, the amount of memory access from 8.4 gigabytes to 1.8 gigabytes, and each operator pipeline is executed in 1 kernel. As a summary, I would like to show a slide with the results. So at first we saw when we do PCI Express transfers in a naive way, PCI Express transfers take really long, and we can reduce the transfer volume by 8.8 by using this batch processing style and keeping intermediate results on the processor. When we apply compilation in a naive way, we reduce the kernel execution time on the coprocessor, but not to an extent that goes below the PCI Express time. But when we use pipeline prefix sums, we can fully pipeline the processing in each operator pipeline, and we achieve a reduction of the memory access the memory access volume. Reduction in memory access volume was here, and this is the reduction in the execution time by a factor of 11.6x. Okay, yeah. Thank you very much for your attention. The poster session is at 4 o'clock. Yeah, sorry, a bit nervous.
Ask a question. So what are worst case query workloads where your approach doesn't provide much benefit?
Okay, a bad scenario would be a cross join, because we have big thread divergence when elements find many partners in threads. Like at first we implemented only primary key foreign key joins, because then we know we can find the matches in a limited amount of time. But when we have more general joins, then this can lead to divergence, because we have these many execution lanes that can have diverging control flow.
So I'm interested in future work. So like, what are the current bottlenecks, and do you have any ideas how to proceed?
Okay, for the star schema benchmarks, we were able to reduce the execution times on the coprocessor to a level that's consistently below PCI Express. So that's like a good scenario. But for TPCH queries that contain more operators and more complex operators, there are still limitations, and we cannot saturate the PCI Express bandwidth entirely. So that would be could be addressed by improving the algorithms that I used, for example. Other than that, limiting the thread divergence would also be an interesting topic.
Okay, so let's thank Henning again.